is start recording right now. Okay, so we go to the section 12.3. Have we started or not yet? No?
Professor, I had a quick question.
Please.
For the test, are you allowed to pause at any time at all during it? Like if you have to go do something and then
No,
get
no,
back
no,
to
no,
it?
no, 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 no.
No?
It's like,
Okay.
no, it's like a test. It says 180 minutes, and that's just a lot of time for you because
Yeah.
the typical one was just really 100 minutes. So I just added another 80 minutes for extra things that you need to do if you are slower or if you have something that you need to write down the problems. But anyway, no, it's just really the total of 180 minutes. So, and it doesn't give you to pause it, unfortunately.
Okay. Thank you.
You're welcome. Okay. So this is just the new section of 12.3, which is the double integration, and I'm hoping to start the 12.52. So just this is a good way to review one more time what we have learned as of now to just do the double integral. And this is one set of what is limits that we're supposed to write it either in type 1 or type 2. So if that was just really before the polar system and it was just really based on the information in previous, I need room to write it on the right side, previous section. So it says either I can just say x's are constant. So for this problem, if x's are constant, so you have the lowest value of the x is -1, the higher value of the x is +1 because the radius is 1. And then you just have to go from here because you're writing the y, so you walk along the y-axis, so that gives you the upper limit and lower limit. So this is the dx, and then if you want to write the dy, you have to move along the y-axis. So in order to just see what is the first thing that I hit right over here, so that's just really solving this equation for the y. So that would be y equals plus and minus of 1 minus x squared, which tells me the negative piece of the circle because it's below the x-axis, and that is the highest curve that I see, which is the positive piece of the circle. So that means I'm moving from here, which is negative piece, to the here, which is the positive piece, and that's just the limits of integration. If there's anything to integrate, it is just really your integrand right over there. So as we see, if we have such a this radical notation to integrate, usually is the trig substitution, otherwise we can't do it. So that is really a good idea to move it to the new system of coordinate, which is just a polar system, and that makes everything easier because then I don't have to take care of such a this radical notation to integrate. Okay, so if I'm looking to the same problem when I'm moving to the polar, so this is the polar format of that. It seems this is the theta equals 0, and then it's moving all the way to this, right? So this means I have the limits of 0 to 2 pi for the theta, and then for the radius I have to move the smallest value to the biggest value. So it's always moving from the origin pointed out to the circle. So means that's the radius from 0 to 1. We like this form because these are numbers. When they are constant, it's easier to integrate, and we know it's just we don't like to go any of the what is trig substitution or methods or techniques that we have learned in calculus too. So this will be easier if we make it to the polar system. So this means polar system gives you all constant, whereas this part is just really making something in variables or type 1 or type 2. Okay, so that's a goal. Make the job easier for the circle or whatever circular region that we have if we move it to the polar system. So I just practice one more time. If I supposed to do this one in type 1, so this is just going to be the breaking point, because if I just get the limits of integration on this part, it's just really starting from the line of x-axis ending by the curve or the circle which has the radius of the two, But when I'm moving here, it will be different because it's starting from the circle with the radius of 1 and ending with the circle with the radius of the 2. So then it's just different from one piece to the other piece. That makes just really one integration and then second integration for the second region of integral, and then this is the third integration. Okay, so this means I have to repeat this integral 3 times, and that's what we don't like it. Whereas if I just really move it to the polar system, that's just moving once. I have to use different color because I use the pink. So means moving once from here all the way to here, right? So this is just really how your angles are in the unit circle. So moving all the way from here, so that gives you from 0 to the pi, because that's the limits of the x, and then sorry, limits of the angle for the d theta. And then if I'm moving to the r, since is always pointing out from the origin, if I can use the different color, like just really purple. So then it's just starting from here and then ending to here. So it's starting from radius of the 1 and ending by radius of the 2. And then I have to know what's the integrand, which is just really the lecture today. So this is when you have the polar. So when you have the polar, these are constant. But if you want to write it in type 1, type 2, you really need to do 1, 2, and then 3 times of integration, which is a lot of work, okay? So we want to make our job easier for this type of the region, which is usually circle form. Usually it's just somehow in polar system. So that's the goal of this section. Is there any question about this?
No.
Okay, so the only thing that I need to remember from the previous course from the polar is if I give you x, y coordinate and your plan is to write everything in the polar system, the set of equations that you need is r to the second is going to be x squared plus y squared, and then theta is the tan inverse of y over x. And then if I give you the polar and the goal is to transfer or convert to the rectangular coordinate, so then x is r cosine and then y is r sine. So this is two only set of formulas that I need to remember from previous course. So whatever is right there has a coordinate of x, y, so can be written in terms of r. What's the r? Is the distance from the origin. And then if you have the angle is just really always starting from here to be 0, and then it's just with the positive part of the x-axis. So that's all I need from the previous course about the polar. But then whatever else I need, I just really need to teach you here again, because it's just based on the graph of the functions that we will see in this course, okay? To define any type of integration, we have done 2 types as of now. This is the 3rd type of integration that we do. So it's always the process, the same thing that is, as I said, you have to chop your region to the pieces, and then out of those pieces, you have to take one lucky point, and then you have to define what we call a Riemann sum. That gives you a new type of integration. So this is always for defining what we call the new type of integral, which, as I said, from the preview of this course, we have had by now 3 of them. We will get another 5 sets or types of problem, which the process is going to be always chopping to the pieces, pick a lucky point, and make a Riemann sum. Then you have a new type of integration. So this is how we define, right? So we have to start with the rectangular region, but rectangular region in polar is not really like a rectangle, it's like a sector. So the rectangular region means your theta is constant. So to be constant means you are moving between 2 lines like this. So this is the to be constant for the theta angle of between alpha to beta. And then if you want to have the radius to be constant, it just really means between 2 circles. So radius is constant means you are between 2 circles. So as I said, this is what we call rectangular region in polar, because all boundaries are constants. Constant for radius means circle. Constant for the angle means that that line, that slant line. Okay. So the goal is, as I said, chop it to the pieces and pick a lucky point and make a Riemann sum. So chopping to the pieces here means what? So you have had the interval from A to B, so then you chop it to the pieces in R direction, right? So you start to chop it to the pieces in R direction. That makes it right here to be these pieces. This is in R direction. And then you have to just make the same thing for the theta direction to make it to the pieces. So then you start to chop it in this direction. Okay, so that is chopping in two direction of R and theta. So then you pick just your ith piece. So you say, this is my ith piece. And again, the thing is, I have to remember this ith piece is not a rectangle to get the area, huh? So this is just really something like this. So which is not a rectangle region to directly say, okay, so that is giving me the delta theta, that is giving me delta R, so then product is just giving you the area of that piece. Is not, right? Because that's not true. So this is just really finding the area of these pieces, because that's what I need for integration. Okay, so this is what I have had after making to the pieces. And then for each piece you have to pick a point. So for now, pick the point. We just make it to be middle point, right in the middle. So this star point is right in the middle. But again, we know there are many options, okay? So in order to get the area of that piece, which is, as I said, is geometry, is sector, area of the sector. So one thing I need to remember from the previous or simple geometry is the area of sector has to be like this. So means if I want to get the area of the sector, I have to have what was this? If I want to get, sorry about that. If I want to get the area of the sector, the geometry says that should be half of the radius times the central angle. Half of the radius times the central angle. If you don't remember what do we call a sector, so sector is just this shape. This is what we call a sector. Oh, I forgot to change it, right? So this is going to be the radius, this is going to be the angle, but the area of this sector is going to be half of radius squared times the central angle, okay? So in order to get that little piece right over here, so what I need is, I'm going to just show it right over here. So the area based on the geometry is going to be area of this big sector, which I make it with the green, and then minus this small, I think the blue is not a good idea, I just need it darker. So just this sector, right? If I subtract the green one minus the blue one, that would be that little area that I need, okay? So if I just want to make it by geometric region, so this should be the area of the big one minus the area of the small one, okay? So this is area of large sector minus area of small sector. And then when we just do a little bit simplification, because we can factor half, we can factor delta theta, so that gives you difference of squares, and that difference of squares just factoring out in this way. So this piece is going to be delta R, and then I have delta theta, and then this half was really what we call R, okay? Do I need to know what this prove over here? Actually, for calculation, no, you don't need it, right? So for calculation, it's just giving you the reason why whenever you are moving from this what is XY coordinate, and you try to write it in polar, you do have always this extra factor right over here, okay? So this is just geometric reason, sorry, behind of this extra factor, we do have always in all type of polar coordinate when we just do it as shortcut for integration. Okay, all I need to know from here, if when you make the pieces to be more and more, you can move it from easily what you call what is it, xy coordinate to what we call polar coordinate by just remembering it's not dx dy exactly equals what we call dr d theta. It does have that extra factor of the r. And why that extra factor of r is sitting there is just because of the area of the sector, because of the geometric reason I have explained right over here. So that r is always sitting when you are transferring or you are finding the area of the sub pieces that you have made. Okay, so here delta x times delta y is making the delta a when you are in xy coordinate, but when you are moving to the polar, the area is not just length times width, it's just r times the delta r delta theta because of the shape. Here is just really one rectangle pieces, but here was the pieces like this, which the area looks like has some extra piece of r, sorry, factor of r. So then what do I need to know from all this is just really the entire transformation or conversion from x to the r cosine, y to the r sine, and dA looks r d theta. That's it. Okay. So that's just really the reason we have that extra factor of r. And then we are interested to do for circles because that's just easier when we have circles in polar system. Is there any question? Okay. So this is the first example to try. How do I know it's easier to go in polar? How do I know it's easier to go in polar? As I said, first of all, for the circles, right? Because I have one circle for the region of integration, another circle for the region of integration. Another reason is because of this thing, right? If I have a radical and then under the radical I have x squared plus y squared, that's just a lot of work for trig substitution. So that has to be a polar system. That has to just write down in a polar system because that makes it really like 16 minus r squared. So that's why we prefer to go by polar here. Is there any question here? Ready to do this problem? Are you ready?
Yes, we're ready. Yeah, let's do it.
So first thing is region of integration. What's the region of integration? It says you have to make two circles. One of them is radius of 1, the other one is radius of 2. So I just make it, oops, again, I forgot to just change it. Still have my eraser. So this is radius of 1, this is radius of 2. As you see, since it says upper half, so that's why I just make the half part. So that's just the region of integration for me. And then I prefer to go with the polar. Actually, we have done similar thing on top when it was just introduction to this section. So when we go by polar, we have to remember just really is like unit circle, right? So the unit circle theta started from here to be 0 and it goes all the way to this direction. And that's just how it's increasing and it's always positive. And then the radius is always starting from the origin as increasing because it's distance from the origin. So that's how the radius is increasing. So if you use these arrows, hopefully you won't have any problem. Okay, so the limits for the theta, what is it? Zero to pi, because I have started from here and I just have to move all the way to here to just really cover entire shaded region. So yes, it is 0 to pi. And then the other one, which is just the radius, it's always pointing out from the origin. You have to start here because that's the beginning part of your shaded region, and then you have to end it here, which is that's the end point of your region. So that would be from 1 radius to 2 radius, and then the r. And then that's extra factor of the r is always sitting there, and actually that has a name. So this is later in this chapter we call it Jacobian. So Jacobian is the extra factor for changing any variable. So this is changing from xy coordinate to the r theta coordinate. So if you change any variable like u substitution that you have had in the other course has actually Jacobian, but we didn't know that's extra du is the Jacobian. Okay, any changing variable that we do in the integration has a extra factor of the Jacobian. So for this one, r is Jacobian or factor that you need to add for moving from xy coordinate to the r theta coordinate. Okay, and I did just this changing right over here to the polar. So what I have had was integration of 16 minus r square under the rad, and that's just your new integration. Okay, so this part is a u substitution. I usually skip the steps for this integration. Always encourage you to do that thing. So this is what you need to do in your mind. You practice to do in your mind for this little u substitution here. So you call u to be under the rad, and this is 16 minus r square. So then the derivative is going to be minus 2r and then multiply by dr. So then integration that I have had like a square root of 16 minus r square and then 1r and then dr turns to be square root of u and then du divided by negative half, or just 1/2 is outside. So negative half is outside, so I will have u to the power of 1/2 plus 1 divided by 1/2 plus 1, right? So this process is just really something I encourage you to do in your mind, and then write the answer for me. So what is it? 0 to pi. And then I have had this process of integration right over here, which is negative half, which is u 16 minus r square is my u, 1/2 plus 1 divided by 1/2 plus 1. And then I just plug in by the value to be 1 and 2, and that's just the next term for the theta. Are you okay with my u substitution?
Yes. Yeah, it makes sense.
So we factor every of these things we have inside because they are all constant. Negative half is a constant. Reciprocal of 3/2 is 2/3 is a constant. If I plug in the value 16 minus r to the second, so it's the value of 2 to the second. So this is replacing the value of 2 to the second. So this is just a constant to the power of 3/2. And then this is 16 minus the value of the 1 replacing. And then this is to the 3/2, and that's just a constant, okay? So the only thing left is just one integration in terms of the theta, which is actually a constant, okay? So which is actually a constant. Let's say I have integration from a to b of nothing, right? So that's just really end point minus a start point, right? So this is really same thing right over here. So let me make it lighter. Yeah, the same thing right over here, because that's just means theta, and then you plug in from 0 to pi, and that gives you exactly pi, huh? So that is still one thing that you can skip, because it's basically the integration of 1 And in terms of theta, is going to be theta, and then you replace end point minus the start point. So it's really the length of that distance, the length of that limits of integration, which is pi minus 0, and that gives you pi, okay? So then if I want to write the result, I will have 1 pi because what I said right now, the extra factor of phi that you have to multiply, the 2 by 2 cancel out, so it's just negative 1/3. This is 16 minus 4, which is 12 to the 3/2. 16 minus 1, which is 15 to the 3/2, and that's it. That's the answer. Any question?
Oh, no, I think that problem's good.
Mm-hmm. Move on. Okay. So next one. This is the next one. What it is finding the volume. One more time, this is the volume that we have learned in the first section. It says you have to get the double integral of some surface, which is just the top of your what is solid, and then you do have something which is the region of your integration, and that's just the base of that surface, okay? So for volume, you have to have one three-dimensional graph that gives you what is the integrand, and then you have to have one two-dimensional graph that gives you whatever is just the limits of integration, okay? So for this one, I'm just going to, again, start to graph it from the beginning. So this is going to be your paraboloid right over here, which is just upside down paraboloid. This is upside down paraboloid right over here. And I know this radius is 1. How do I know? Because that basically means you set the z value to be 0 in the paraboloid, and that gives you the circle with the radius of the 1. So the level curve at the radius at the z equals 0 is going to be exactly the circle with the radius of 1. So this is going to be the base. This is going to be the base, or just the one that you needed to set the limits of integration. So I'm just going to bring it down here and to make it in two-dimensional. Okay, so this is 1, and that's exactly what I need to set the limits of integration. Okay, so this is x, this is 1. So this gives you the limits of integration, and three-dimensional, if I just write it, this is the roof or top, which is 1 minus x squared minus y squared. Why I wrote it like this? X squared minus y squared. If I just write it in polar, it's the same as 1 minus r squared. Okay. So give me my limits of integration starting most of the time, 99% of the time in this course, theta is first. Which one is always first? The one which starts with the constant, okay? But at least in this course, for most of the problem, theta is the one which is a constant. It doesn't mean we can't have the other type, we do, but that's just really for us for now to make it just unique for most of the problems. It's just starting with the theta most of the time, okay? So let's just say again one more time. This is theta equals 0 always, and that's how the unit circle is increasing the theta. So 0 to
2 pi.
Entire circle is covered, right? So 0 to 2 pi means entire circle is covered with this shaded region. Then you have dr. So what is the limits of dr? I'm just using
0 to 1.
colors. So just from here, 0 to 1, right? So then again, this is how you always make for your dr, pointing out from the origin. And then how you make it for d theta, you just go it round, like just how your unit circle is increasing. Yep. So that was just from 0 to 1. And then I have had the extra factor of r right there because of the Jacobian, because of the changing variable. So my always integrand is going to be whatever z is, whatever is the roof, whatever is the top of my graph, because we are getting the volume under the surface. So this is just the, what was it, integrand. So 1 minus r squared. Okay. So that gives me, I think the integration is fine. If I distribute r inside, that would be r squared divided by 2 after integration. If you distribute here is r cubed, so that would be r to the 4th divided by 4. Then you plug in 0 to 1, and the next 10 is for the theta. So that is just going to be constant. So let's just put it out, just really pull it out. All of them is going to be half minus 1/4. I'm not going to plug in 0 because that's just everything 0. So then you have 0 to 2 pi d theta. I really don't want you to rewrite this piece, because this piece, as I explained, is going to be the length of the interval. So which we have started from 2 pi. So it's just really 2 pi minus 0. So that's just how it is. Okay, so this piece is not really required to write. If I was, I just directly write on top. So that was 1/2 minus 1/4 times the 2 pi, and that would be enough. I mean, it's just okay to skip this step. What was the step that I skipped? Integration is going to be theta, because it's just really 1 in terms of the d theta, and then that's just upper minus lower limit, so that gives you 2 pi. So if you skip it, that's just really the answer. What was it? Pi over 8, huh? Pi over 2. Fine. Move on. Should I move on?
Yes. Yes, you can go on.
No question. Okay. So these are the details for the same problem and the same calculation. Okay. This is just remind us one more time for the same problem that we have done right now. If you're supposed to wrongly do this problem by rectangular and didn't change me, sorry. And then you just make it in type 1, which means this is the limits of the x, because that was the graph, right? So you have had just a unit circle. Oopsie, why my circle is. So this is, sorry. Okay, there. So then this is just going to be from -1 to the 1 for this, the x direction, and for the y direction is going to be from here to here, which means you are moving in this direction, and then you're moving from negative piece of your circle to the positive of circle. But that's just really a lot of work, because when you plug in, this is what you're supposed to integrate at the end. That's what we don't like, because it must be trig substitution and it takes time. So that's just what we don't like to do it. So that's why we go bipolar, and then it's just really one easy calculation. Okay. My next example, actually, it's a nice one for several reasons. So first of all, this is the first time that you have two z's. So means you have two surfaces. That's a nice problem. And the other one is because if you make the graph, the radius is what is just, you have to compute it. It's not given to you. Okay, so that's just, and then even the integration is nice too. So this problem is a really nice one. Okay, so again, it's finding the volume. I remember if I want to get the volume, I need to have two graphs. One because of the three-dimensional that I need to set my integrand to be, and the other one two-dimensional because of the region of integration. Okay, so for this problem, since I have two surfaces in three-dimensional, I have to remember same rule that we've seen it in the other course, which is just finding the area, is really same over here, which is, if I just remind you, in the other course, when you have had, I mean calculus 1, when you have had this area between two curves, you just say, I have to say y top, and then subtract from y bottom, and then this is y top minus the y bottom, so that gives you just the area between two curves, right? And then it's really same idea when I'm just moving to the more dimensions, when I have to get the surfaces and then the volume between surfaces. Let's see, this is my z top, and then that is something that is z bottom, and then this is just what I'm finding. So this is just the volume between these two surfaces. So then it's just going to be your integrand is whatever is bigger or is higher or is the top minus whatever is on the smallest or is on bottom. So that's z top minus z bottom if I have two surfaces. Why I did not have this problem for any of the other questions that we have tried? So if I go back to, for example, this one, so the top piece for this, so your z top was just really 1 minus r squared. So, but the z bottom right over here, so your z bottom piece was just really xy plane. So that's why you didn't worry about why I don't subtract them, because the top piece is right here, and then subtract 0, it doesn't change anything. So that's why I don't have to worry about the base or the bottom of my surface, because the bottom of my surface was 0. The bottom part of the surface was 0, so you were fine. So that was just really one surface given to you. But here, since two surfaces is given to you, you do have both of them. So whatever is bigger is sitting on top, whatever is smaller is sitting on bottom, and then you have to subtract to get the volume between. Okay, does it make sense by now? Question? Is there any question?
No.
Okay, so let's just start to graph it. You have had one sphere with the radius of 3. Okay, and then the other one was the cone. So I make my cone nicer because I have to erase the sphere anyway. All right, so this is just going to be the cone. This is going to be the cone, and then if I just say what the region or the solid is, it says it has to be above the cone. So this is above the cone, and then it has to be below the sphere. So it has to be below the sphere. So this is the part that I'm looking for. So we just say, if this is the ice cream cone, you want to get what's the volume of your ice cream. Okay. I'm going to erase the extra pieces because I am just looking for this volume. So again, three-dimensional graph says the top is the sphere. Okay. And then the bottom is the cone. Okay. So this is for three-dimensional or for my integrand, but the problem is I kept this one right over here to be my biggest, radius of the 3, because remember, if you want to get the two-dimensional one, you have to look at to the shadow, huh? So I'm going to bring my shadow to see what I get, right? So this is going to be the shadow of the graph, which the radius, obviously, that's just what we needed for set the limits of integration. But as you see, the radius is not really as big as the 3, it's really smaller. Do we know how to get that radius? What's the radius? That's the question. What is the radius right over here? How do I find that radius? Any idea? How big is this radius?
Would it be 3?
No, it seems that the 3 is just
Because I'm
regular.
thinking plugging in the z, which is equal to square root of x squared plus y squared, into the equation of x squared plus y squared plus z squared equal to 9, and then solving for r.
Z top intersection. Yep, exactly. So it seems this is really intersection of these two surfaces, huh? Set them equal, because that point is exactly intersection of two surfaces. So you have to set these two equations equal, and that is just really square both sides. That gives you 9 minus x squared minus y squared equals x squared plus y squared. So then you have 9 on this side, then you have 2 copies of x squared, then you have 2 copies of y squared. So this is really the equation of circle, and that's just the radius, right? So radius is 3 square root of 2, because that point is the intersection of two surfaces. And then what does the intersection mean? Set the equations equal. That gives you the radius that I'm looking for. Does it make sense?
Yeah, that makes sense.
Okay, so that's it. We are ready, right? So we can set the limits of integration of, what do I have? The angle is the first one, since it's going to be really a full version. So it's just really from 0 to 2 pi. It's all the way from the 0 to 2 pi because it's a full circle. And then the radius is just from 0 to 1. So radius is from 0 to 1. And then that's extra factor of the r because of the Jacobian. And then, as I said, you have to put z top minus z bottom. Z top is your sphere. So again, this is z top minus this, the bottom piece of your surface, okay? And then that is going to be like this, okay? So I'll go back over here and I will rewrite one more time. This is the z top, which is 9 minus r square, and this is the z bottom, which is r square. And then actually I can just write r itself. I don't have to write it the square root of r, because r is always positive. So this is r. Okay. Then integration. Then integration. Again, that's one more time that process that I have done, and I encourage you to do in your mind the u substitution thing. You don't need to do all entire here. So this is a u substitution. So what I'm talking about is the piece that has a square root of 9 minus r squared. Then I have r, and then I have dr. So this is what you need to do in your mind, and you need to practice to save your time. So you take your u to be 9 minus r squared minus 2r dr is your differentiate. So this is to be minus half outside square root of integration of a square root of u du. So that gives you minus half outside. So this is going to be u to the half plus 1 half plus 1. So this is what I don't want to see in your paper, and it's just really saving your time. So then I have to go by here and say this piece right over here was u to the power of half plus 1 divided by half plus 1, and that extra factor of negative half because of this derivative, minus r is here times the other r here, it gives you r square, but the integration is r cubed divided by 3. And the whole thing have to plug in by 0. Why no one to say this is not 0 to 1? I'm so sorry, guys. This is not 0 to 1. Okay, so I'm just changing in the color. So this is going to be 3 over 2. This is 3 over 2. Am I right? I have just had the radius is here 3 rad 2, but I did not plug in here correctly. It was 3 rad 2, and then it goes here too. And that turns is not really nice number, but that's it. That's what we can do. Okay. Is there any question about the process? I'm going to give you the break right now. Is there any question about the process?
No, this is really cool.
Okay, great. So if not, let's just have again about 7 minutes. So it's 31 right now for my PC. So let's say 39, right? So 3:39 we will start, okay? If you have something to grab like water, restroom, so let's just start it after 7 to 8 minutes. But we are here, you can talk to me. Okay. So let's go back to this once more. Where we were, so let me just, okay. And I did nothing, it's just really same thing with the ugly numbers. I'm not going to simplify, it's fine to be like that. So this is the answer. That's just really one more time to remind you, this piece is just one more time to remind you, you most of the time in this course you start with the angle of the theta first. Why? Because the angle is constant. So you might have radius to be between two curves. That's just really possible. So if you have really two lines like this, which is your angles are constant, and then if you are moving along the increasing direction of the, what is it, the R, so this should be your lower limit and this should be the upper limit. And that's just, if you call it type 1 or type 2 is fine. There is no just really name. We don't need, I mean, there is a name, but we don't need to know the names, okay? So this is similar to the type 2 in rectangular region. And you might have the other one, but that's not really in this, oopsie, that was just two-dimensional. Well, you might have the other one, which is when your radius is constant, so it's between two circles of r equals a, r equals b, and then maybe your angles are between two functions, and the angles are between two functions, but that's not really common in this course, at least it's not common. If the region is looks just really like between these two, since the r's are the constant, I have to start with the r equals a to the r equals b, that's the region of r. And for the angles, I will go what it is, the way that the angle is increasing. Angle is increasing in this way. So this should be the lower limit theta 1, the upper limit theta 2, but it has to be in terms of r because it's just the r is the constant one, okay? And then you put the r or whatever function you have, okay? So this one that I made it on right side is not common, we don't see it that much, but the left side is just what we have done a few examples. We have started always with the angle, and that's just similar to the type 2. So you can call this one type 1, but that's not really what you see in this course. So they are always like whatever is on your lecture note, the type 2 thing, okay? And one more time is reminding you, when you were in calculus 1, calculus 2, sorry. So that's just calculus 2 in section 10.4, you have learned how to get the area by using polar, when you have a polar equation, your polar curve. So that was just really one formula. But here I don't need to know any formula. Here, as long as I know how to set the limits of integration, that tends to be exactly the same thing, okay? So when I have to write the area between two constants, maybe alpha is here, beta is here, and then just some curve is right there, and that's just the goal to get the area here in polar. So then I will set the limits of integration as I have learned for the theta first, because that's the constant. For the radius, I start to move in this direction. I just say starting from the origin all the way to whatever is this endpoint is called to be h here. I'm going to call it the same thing. And then it's just from 0 to h of angle, and that's just really what I call Jacobian. And then I just start to integrate from nothing, right? So this is what we have learned. If your goal is to find the area by using the double integration, if your goal is to find the area by using the double integration, you do not have any integrand, okay? So then this is just really what I have, and it turns to be exactly the same thing that we've seen in the previous course, or 10.4 or whatever, is just find the area by using the polar, because this is just when you plug in the limits after the first term integration. So that's just what we've seen it in previous course, radius squared divided by 2 and in d theta. Do I need to remember the previous course formula? No. What I need is what I've learned over here. So this is what I need to remember. In this course, I have learned in order to get the area, I must just do the double integration of no integrand or 1, and then as long as I set the limits of integration and start to integrate, I will get the area. So I'm fine. Okay. As an example, we get just to find the area of what it is, this curve in polar. Again, if you don't remember how to graph it, it's fine. At least for this setting that we are doing right now, everything is just really at home. So you have access to the graphing calculator or just you have access to your Google, so you can always graph it. Even if it wasn't in this setting, and if I had to set somehow the quizzes to be through the Zoom or some other setting to do the testing, this type of graphing that we're supposed to learn in Calculus 2 is fine if you don't remember. And then I will provide this graph, exactly what I'm talking about, this graph, because this is just the steps usually teachers from the previous course, they don't have time to finish it, so they don't cover it. So this type of graph, which is just the R equals cosine of theta, and there are several of these nice graphs that is at the end of our Calculus 2. So what is in this course is just to get the area, to set the limits of integration in double integration. So that's what you need to know, okay? But not about the graphing. So since this is just what the question asks us to do, one more time, find the area with one loop of the 4 leaves rows, okay? Ready? Give me my limits. So area is going to be double integration of 1dA. Theta is from here to here, right? So this is from negative pi over 4 to the pi over 4 based on the graph. Angle and then radius is moving from here all the way to his leaf, huh? So it's moving all the way to this leaf, and that's just whatever is just the equation of the rows, right? So it's just moving from 0 all the way to the cosine of 2 theta. So this is just R. And then no integrand, right? So that's just really 1, because if I'm finding the area, there is no integrand. So this is confusion most of the time, because we are getting to the triple integration. Area needs to be blank, or is integration of nothing. Volume needs to have something, right? So you have to have a surface or roof or bottom to integrate, but just when you do the double integration, because we do the same thing in triple integral too. And then that's it. So you have to go from negative pi over 4 to the pi over 4. And this is just R squared divided by 2. You plug in 0 to cosine. And then that gives you from negative pi over 4 to the pi over 4. And again, I prefer to factor my constant, which is half. And then cosine of 2 to the second. 0 is just 0. Okay. Okay. One more time. I have something to remind you from the previous course. If you have even power of the sine and cosine, you have to go by half angle formula. So cosine of 2 times theta divided by 2, sine to the second is 1, and that's minus cosine of 2 theta divided by 2. And then if I have odd power of the sine and cosine, So that should be cosine square is minus sine of square. And then I have sine square minus 1 cosine of square. Okay. So this is half integration from negative pi over 4 to the pi over 4. And what I need is just, this is even exponent. So this is even exponent. So that should be this formula to plug in. Okay. So I reminded you because I needed right over here to plug in 1 plus. Actually, that is twice, right? So you have, if I just make it darker to be clear. So if it was theta, right? So it should be twice of that. Minus 2 theta. So it's 4 times. Oops. Is it fine? Divide by 2. Agree with my half angle formula? And then I can integrate. So I have 1 over 2 outside. I bring another 1 over 2 outside. Integration of 1 is theta. Integration of cosine is sine. Divide by the constant. Plug in the limits. And then that gives me 1 over 4. And then one more time. This part, which you need to plug in pi over 4. 4 times of pi over 4 gives you sine of pi. So this entire piece, if you plug in, gives you 0 because it's sine of 0. Oh, sorry, sine of pi, which is 0. So all I need is just plug in for pi over 4. That was plus. Pi over 4 minus pi over 4. Pi over 2, huh? So it's pi over 8. Is there any question? Do you have any question, any part?
No.
No. When there is anything in chat, I don't see it right away. Okay. That was for before this. Okay. Okay, so the numbers, the calculation is right over here. I have one of those nice problems. Why? Because it has 2 surfaces. And then it's just brand new or nice example because it's not centered at the origin. Okay. So this is the first time that you see the circle in this section that is not centered at the origin. So then it's a nice problem to practice to find the limits of integration. Okay. So find the limits of integration for r and theta when it's not centered at the origin. Okay. So I'm going to make my circle first because that's easier. This is going to be the first thing that I'm going to graph because it's so much from algebra, huh? So I have to divide this number by 2 and then a square and then add both sides, huh? So then this is 1 to complete this square. This is 1 to complete the square because that's just divide the middle term by half and then square it. So this is going to be x minus 1 to the second plus y squared equals 1. So in this case, the center is not the origin, and that's the only difference we have for this problem. So radius is 1 and center is not at the origin. Center is sitting right over here, so I have to graph right over here. Okay. Okay, so I'm going to go back to the problem. So read it from the beginning, what we are looking for. So we are looking for the volume. So volume supposed to be double integration of z top minus z bottom of the dA. And then it has to be under the parabola since the graph is given. So I'm going to show at least here and then make my graph one more time. So it says supposed to be under the parabola. So it's just really starting from here and under. Okay. And then it has to be above the plane, XY plane. So it's just starting from here and go above. And it has to be inside the cylinder. So that's just really what we are looking for. So this is the area of this piece. Okay. So that's the volume we are looking for. I'm going to again graph it from the beginning. That's just to practice what we have done, a few times. So that was the cylinder thing because it is x-axis. It's easier to make it in this way. So that was the cylinder one, which I have made the base right over here. So I'm going to make it in the same color. This is just really what we have done once. It's just really same thing. And then the other graph is just the parabola. And this is my parabola. And then if I just make different highlighter, this is just as we showed in the graph, the volume that we are looking for, this piece. Okay. So if you are ready, let's set the limits of integration. I need to know, first of all, what is the limits for theta. Again, remind you, this is the start point, which is theta equals 0. Since for this graph, you have entire this piece. What's the limit? Any idea? What is the theta right over here? What is the theta right over here?
To find your limits of integration, don't you just, could you set those two equations equal to each other or not in this case?
Not in this case, because this one has the z, this one doesn't have the z. There is no way to set them equal. It doesn't help you. So one more time, to just, it doesn't make sense to be from bigger. So I got one comment, it says from 3 pi over 2 to the pi over 2, but that just doesn't make sense to be in this way because it has to be in increasing order, right? So you can just say, instead of this, you can just say is negative pi over 2 to the pi over 2. So that makes sense, right? So because it doesn't make sense to go from the bigger number to the smaller number, right? So your 3 pi over 2 is bigger. So it's just going to be from negative pi over 2 to the pi over 2. Okay, so this is just the limits of integration. So one more time, because the comment I got from Luke, I think it was Luke. So remember, so you are trying to get the volume, right? And then it should be something which is your integrand and something which is the region of integration. So the region of integration is always the base of the graph. The other word is the shadow of the solid, okay? So do I need to always set them equal to find? If there is two surfaces, yes. So two z's, yes. But if there's just really one, you don't need to set them equal, okay? So you have to always imagine if there is a sun right over here, right? If there is a sun right over here, and then it's just making the shadow of your graph. How is the shadow of my graph? Okay, so that shadow of the graph when I'm looking from the top is just what is the region of integration. Okay, so region of integration, if I go back for the previous setting, it is too slow. I have to go slowly. Okay, so one more time. Right over here, you see if there was a sun or light right over here, so then the shadow of my graph was like this part, right? So that gives me the region of integration, right? So that gives me the region of integration. For this case, wasn't clear because that radius was smaller, so it wasn't clear. We have to set them equal. I don't know whether I need to keep my sums. So should I erase all of these things? Does it help for future? Okay, for this one, I didn't need to set them equal. Why? Because that was just really the base of my cylinder. It wasn't really something that I'm losing the value. It was right there. It was just really the base was the cylinder. So it just really, whatever is the circle base of the cylinder, give you the limits of integration in two-dimensional. Make sense? Is it okay? Move on. So
Yes,
it's
move on.
the shadow. No, I have had something. Sorry, I don't see that comment. I have to go back to this one. Somebody said something. So if the shadow half, is the shadow half if an ellipse? I don't understand the keyboard here. If the shadow of an ellipse. That's not ellipse, that's circle, right? The shadow for this graph is your entire circle, right? So the shadow for this graph, if you go right over here, the base is entire circle, is not half. Okay. Do you see it or no, Ricky? Okay. So then I have integration. Okay, so then I have for the R, which is going to be starting from the origin all the way to here, which is just the endpoint is the equation of the circle. So the endpoint is the equation of the circle. So then I go back and see what's the equation of the circle in polar, huh? So you have to convert the equation of circle in polar. X squared plus y squared in polar is R squared. X in polar is R cosine. So then you have R divide both sides. So this is just the equation of your circle in polar, okay? So you have started from the 0 for the radius, but the endpoint is the equation of circle. The endpoint is the equation of the circle, okay? And then I do have the integrand because it's just really, there is a z in the equation. So there is a z in the equation. I don't know where did I write the z's, but I'm going to write it right over here in the graph. Z top was the paraboid, which is x squared plus y squared. So that gives you r squared right over here minus the z bottom is just xy plane, so it's 0. So this is just going to be my integrand. Huh? I don't know why this keyboard is frequently coming. So that is simply from negative pi over 2 to the pi over 2. So this is going to be r squared times one more r over here. So it's r cubed. Integration is r4 divided by 4. Then you have to plug in this limit. I will do one more step because that gives you a lot of, again, trig simplification. So that is our, what is it, 2 to the 4th cosine to the 4th, and then 0 is just 0, 0, and that's just one more time even power. If it is even power, I have to go by what is it, cosine of 4, cosine to the 4th. So one more time, I just have cosine square equals what? 1 plus cosine of twice divided by 2. So that gives me cosine to the 4th is just 1 plus cosine of 2 theta divided by 2 all the way to the 2nd. Why? Because it's cosine square, right? So it's just 2, one more time squared, right? So this is 4. So half a square is just 1 over 4. But then I have to square one more time. 1 plus twice of first to the 2nd plus 2nd term square. Okay? And then still I did not integrate. I have to integrate one more time. So again, still I have even power. Still I have to use the same formula. That is too much trig simplification. So negative pi over 2 to the pi over 2. 1 is itself, 2 cosine is nice to integrate. So one more time, if I use the half angle formula, then I can integrate. I'm not going to do the next step, okay? So it's just really one more step to integrate. And it's there. You don't have to worry about it. It's really right here, okay? So what I have done is just stopping right over here. And it's just one more time to integrate every single term. And all of them are 0. So you just have the first term. Okay. Any question? Do you have any question?
No, we're good.
No question. Okay. So based on the schedule, I'm going to move to the new section, but it's just really short introduction. And it's just shortly started, and I'm pretty sure I can't finish it. It's just really giving you one time lecture here, and then reminding you one more time on the after the break when we come back, and hopefully it helps to understand. It's so slow, sorry. Moving up. Oh my God. That is too slow. I don't know, does it help if I make it smaller? No. Let's go all the way up. Okay, here. Finally, okay. So the triple integration, I will say, has nothing new. It's just really same process. Only you have one more term, right? So you have done what for the x, then with the y, and then with the z's, then extra what is step that I need to do. Okay, so this is just following same process with one more extra step. So when we do in triple integration, so it's just really when you have done partial derivative for 3 variables, now it's partial integration for 3 variables. So since I have 3 variables, so since I have 3 variables, so you must have a limits for the x, you must have a limits for the y, then you must have a limits for the z. So then your sub pieces, if you follow the same process that we have done, at least 3 times for this course is chopping to the pieces, pick a lucky point, and then make a Riemann sum. So that sub pieces in calculus 1 was only delta x. In calculus, when we do the double integration, was delta a. So those are your sub pieces. Now we are in triple integration, so it's delta volume. So it's just really 3-dimensional sub pieces that it's just the volume. Okay, so you have x's, limits of the x's. So when you chop it to the pieces, so then you will have delta x. And then you have to chop it to the pieces in y direction, so then you have delta y. Then you have chop it to the pieces in the z direction, so then you have delta z. So then each pieces is delta v, or volume of the box, which is width, length, and height. Okay, so then the sub pieces is this time is going to be the volume of those sub boxes. Okay, so then that's just what's going on over here. So that is delta x, delta y, and delta z. So delta x, delta y, delta z. So your sub pieces is little cubes, and then it's just really volume of that little cubes is going to be the sub pieces that I'm looking for. And then I will just make the Riemann sum. So it's just really 3 of them, because I have x direction, y direction, and z direction, and let the number of pieces to be more and more, and that's what we call the triple integration. So to define the triple integration, you have to let that number of pieces to be infinity. So then you got just what we call triple integration. So the triple integration for continuous function always exists, so that limit always exists, but the order of integration is still for the same name, the same theorem extended in three-dimensional cells, so you can reorder them. If you need to make it in different order, that's fine. So that's just giving you the same answer. Can you tell me how many of different order that we can have from permutations? Especially, I think computer science, they have learned these permutations. For the first, you have the option of either dx or dy or dz. So you have 3 options. For the second place, because it's not repeated, you have 2 more left. And for the last one, you have 1 left. So it's total of 6 different orders that we can do this integration. 6 different orders that we can do this integration. All of them are equal. Obviously, we pick the one which is easier. So we can pick the one always which is easier, but all of them gives you by Fubini's theorem the same answer. How do we do the triple integration? Exactly, we start from the inside. So first we take care of whatever is the inner one. So if the inner one is in terms of the x, means you have to keep the y and z to be constant. So inner one is just in terms of the x, the other 2 variables has to be constant. The next one has to be the y. So the next one has to be the y. So then the z must be fixed or constant. And then last term is the z, and it has to be end up with the number. So then the question is, if I do the single integration of a function in 1-dimensional, give me the area, sorry, actually it's in 2-dimensional, but it's single variable. And then if the double integration of the 2 variables function give me the volume, so what would be the triple integration of 3 variables? This is in 4th dimension. I don't see it, right? So this is the 4th dimension, which I don't see it, and then it's called hypervolume. Okay, but it's nothing that we see. Fine. Okay, so let's practice with the numbers. Okay, so we have to see if it is just dv is on my hand to choose whatever order I want to do. So it just really doesn't matter because this is a constant, so all of them are constant. I can just do whatever order I want. Let's just start with one of them. So there are really 6 different orders that we can do, either one gives you the same number, okay? And since a polynomial, so and all constants, so it doesn't matter you start with which one. So I start from the x to be the outer one, so it's from 0 to 1. And then I change the highlighter color to show you what's my next based on what is written over here. So this is the y. So that is the next term, which is from -1 to 2. And then the last one is the z, which was given to be from 0 to 3. And there was a x and then y and then z square inside, okay? So by this order, by the way that I wrote, again, it doesn't matter which order, but the way that I wrote, I want to take care of inside first, right? So I have to take care of always starting from very inner one, right? So that is in terms of the z. So if it is in terms of the z, then x and y are constant, right? So x and y are constant, so you just do it for the z part. So then x and y are constant. Z in terms of the z is z cubed divided by 3. Sorry, z square is z cubed divided by 3. So then it goes by from 0 to 3. So this is dy and this is dx. So I have to keep the outers as they are and then plugging the value. I'm going to factor the value out because that's just constant, right? So let's just put this value of z cube, means 3 to the third, divided by 3 minus 0 divided by 3. Okay. This is constant, I just factor it out. And from now it's just really my previous two sections, right? So it's a double integration. I take care of y and then x based on the order that I have decided. So this is 27 divided by 3, so it's 9. And then I have to keep the outer is just x. The inner one is in terms of the y. So then I have to say which one is constant. So this is just the y. So x is a constant. I keep the x to be there. Y is y squared divided by 2. So then you have -1 to the 1, then dx. So that gives me 9 outside. Divide by, okay, y squared. So it's 2 squared divided by 2 minus -½ squared divided by 2. So that's for the y, and the last term is for the x. And that was 9. 4 divided by 2 is 2 minus half. And then x squared divided by 2 is the last one because of x dx. 4 minus 1. And then this is 1/2 minus 0/2. Okay. That's not hard, is it? Any question? Oh, I have to stop here. Okay. Just for practicing, you can just reorder to see what happened. Just remember, whenever you reorder them, so you have to keep the limits as this is the limits for the z, this is the limits for the y. So then for reordering, remember, just really reorder with the limits, not just really the x, y, and z. So whatever it goes with the z, if you just put it outside, it has to be all outside, okay? So don't forget to just change the order of your limits at the same time with the x, y, and z. I'm going to stop here. So that was just really a short introduction to start it. And that would be really great. We have to just try the triple integration, and then triple integration by this step is going to be from 12.5, but the rest of them is really like the previous. So as I said many times, this chapter is entirely connected. So if I just learn one section and then the next section is a shortcut or better way or just somehow is related. So maybe just only one problem, you will see really giving you one problem would be enough for you to test an entire chapter, because that's how they are connected. Any question for me? Do you have any question about the course? I mean, the topic that we covered? Because I'm going to stop recording right now.
Oh, we're good.
Okay.